Good morning, class. I hope everybody's doing okay today. Everybody in the downward spiral towards final exams. Like I say, I will have a announcement up either today or tomorrow. The reason I have to take a little time to adjust for the final exam dates is that we often have dates when grades are due, and what I want to try to do is make sure that if grades are due by a certain point, I can give you as much time and flexibility for the final exam. And there's a little bit of contention about what that date actually is for this term. So once that's finalized, I'll be able to have the announcement up for you. What I want to do today is to continue with the induction process and also cover the binomial theorem. Uh, the attempt at trying to do more examples of induction will help you in the long run because the induction examples will just give you a little bit more confidence. And I have an example here that uses the binomial like we have done in the previous examples. So just remember, as we get into the final topics of the course, as you start reviewing, look at your old finals, go through those, work through them, just kind of refresh yourself with a lot of the information that you already know, just to make sure it's up there. And we will do some review next week. But again, I appreciate your hard efforts. I know that math, STEM math is difficult. It'd be nice to be maybe a non-STEM major and taking a survey math course, which would be much less difficult. But you are pursuing greatness, so I'm going to try to help you get there. So let's go ahead and let Professor Ron share his screen, and we'll look at an induction example. And the reason I'm doing this is because I get, by virtue of the fact of the types of questions that I get, I think, okay, well, students are having a little bit of problem with this, they're having problem with notation or whatever. So I want to go ahead and do this review example. So this is going to be like the ones we've been doing, but using the binomial theorem. Now, in your homework, you might have a list of logical statements about natural numbers, and they'll say, are these true? Are these false? And if they're true, prove by induction. So here's an example of that. For instance, we have n cubed, and I'll write it out just in words, minus 6n squared plus 11n is divisible. This is like the multiple problems, is divisible by 6 for n greater than or equal to 1. And here's what we're going to do. If true, that is, if true, I mean, you think it's true in quotes, prove by induction. Now, like I was saying before, there are times when you can check a few numbers and say, well, this falls apart. It's like the formulas that produce prime numbers that were algebraic. They never worked. So that's okay. So what we want to do is look at this, and you don't, this is a really, really interesting expression here. This is just a third degree polynomial in n. And so you could try to attack this using techniques we've already worked on. But I think you're going to find the induction process is very straightforward. So let's just go out on a limb and say, okay, we're going to check 1 and see if it works. And then we'll say, okay, let's just kind of go out on a limb and try to do the induction step. So we're gonna be positive. We're going to affirm in the positive and let n equal 1. Maybe we just get lucky and the induction step will fall apart. So we'll have 1 cubed minus 6 times 1 squared plus 11 times 1. Okay, well, this isn't too bad. We have a 1 plus an 11, that's a 12. And of course, this is just minus a 6, which gives us a 6. And clearly, 6 divide 6 using the notation that I introduced last class. So remember, S is going to keep track of all the natural numbers for which this is true. So we'll say 1 is in S. That is, P of 1 is true. So remember, as I said before, S contains all the natural numbers for which this statement is actually true. P of 1 is true. Now, of course, we could check 2 and we would find that it would work. Okay, so looking at this polynomial, we're thinking divisibility is not maybe as stringent as producing a certain type of number, for instance, like a prime number, which would be a lot more restrictive. So we're going to go out on a limb. 2, we're going to say for some natural number n, we're going to assume that n is in S. What does that mean? Well, it means that this expression is a multiple of 6. It's divisible by 6, so it's a multiple of 6. So we'll use the same song and dance. This sounds like a broken record, like Professor Ron. So what we can do is say n cubed minus 6n squared plus 11n is just 6 times some natural number. We'll call it 5. Use any letters you like. It really doesn't matter. It certainly doesn't make it correct to use a different letter or make it wrong to use another letter, etc. So when we look at this, we're thinking, okay, so we're doing the arbitrary part. We're picking some natural number for which this is true. This is the induction hypothesis. And so now what we want to do is look at the next natural number. That is, if we look at the very next natural number, which is n plus 1, and we cube it, this is where we get to use the binomial theorem from week 1, minus 6n plus 1 squared plus 11 times n. Okay, so at this point, well, of course, n plus 1. So at this point, we're thinking, okay, if we expand, and this is how we're thinking about this, if we expand, we should be able to recoup this expression because we've got the ends here. And then we can use our induction hypothesis. So remember, if you don't use the hypothesis, you didn't prove the result by induction. I'm not saying this is the only way to prove this result clearly. So now, what is this going to be? Now, we'll use our binomial theorem from the first week. So we get n cubed plus 3n squared plus 3n. And we'll talk about where these coefficients come from, aside from just brute force multiplication soon with Pascal's triangle. And then, of course, we have minus 6 expanded n squared plus 2n plus 1. Move the cursor over a little bit. And then plus 11n plus 11. Okay, so we'll multiply this out. So we have n cubed plus 3n squared plus 3n plus 1 minus 6n squared. Now minus 12n right here, minus 6, and then we have plus 11n plus 11. So all on this line, all I did was just multiply these out. So that was very easy. So what we want to do is recoup this because we know this is part of our induction hypothesis and it's very important. So we can see we have it right here and then here. So this is induction hypothesis. Remember, as you do your test work support your solutions. You don't work backwards from the answers. You do the problem and then you say, okay, I've got a solution here that I've deduced, and you say, oh, that's answer C. Some students are thinking that they can just shortchange their work and that's going to be sufficient, which is absurd. Okay. And most of you all know that. The majority of you know that. So again, remember that as per my instructions, an answer without support, an unsupported answer is a wrong answer. Okay, so just keep that in mind as you continue to do your work. I know most of you know that, but that tends to be something that students think they can get away with. And that clearly is not the way a STEM math class is run. So please keep that in mind. So now let's collect all of that. So this is n cubed minus 6n squared plus 11n. We know what that is, so we're going to section it off. Now let's just keep track of all the ones that didn't have the blue line pointing at them. So we have plus 3n squared plus 3n plus 1 minus 12n minus 6 plus 11. Okay, so now if we look at all of this, we've got a negative 9n there. We only have one of the n squareds. And then here, not surprising, we have a 12 minus 6, which is a plus 6. So that's just collecting the extra terms. Very easy algebra, but very important algebra. And then, of course, this is 6 times 5. So here we have equals, equals. And now, of course, we can factor a 3 out of these terms. Now, of course, this will factor. Don't we wish all of our quadratics were that simple? So we have an n minus 1 and an n minus 2. And then, of course, the sum is the middle term. So the beauty here is that these are consecutive natural numbers. One of them, which must be a 2, an even number, have a multiple of 2 in it. So this could be even, this is odd, or this is odd, and this is even. In either case, n minus 1 times n minus 2 is a multiple of 2. So we can say this is 2 times alpha, where alpha is a natural number. Again, just using basic number theory. Remember, we're calling general math number theory now because that's really what you learned. And you were probably better at arithmetic when you took general math if you weren't using a fancy calculator. So now we have 6 phi plus, now we have 3 times 2 alpha, so that's 6 alpha. So that's 6 times phi plus alpha. And that's clearly a multiple of 6. So this implies, indeed, that when we look at the next expression that includes the consecutive integer from n, that is n plus 1, it's also a multiple of 6. So n plus 1 joins n. We assume n was in S, that is P of n is true, and using that, we see that P of n plus 1 is true. So by induction, S is all of n. That is, P of n is true for all real numbers. So I thought this would be a good example just to go back over the basic constructs that we've been doing with induction. Now, induction is not the end all, okay? It is a nice, discrete method of proof that is very convenient for STEM majors, especially those that go into engineering, because you're going to have to do coding, computer science majors, computer engineers. I mean, coding is part of what you're going to have to do. And so these discrete topics turn out to be very, very useful. Everybody uses induction eventually. And of course, I have students that say, well, it is kind of strange, Professor Ron, but just remember, this is all based on the fact that every subset of the natural numbers has a least element. That's called the well ordering principle. And because of that particular axiom, this method is valid. And you can see that it is much more affirmed to be able to do the abstract approach and cover every possibility as opposed to checking an infinite number of cases, which is impossible. Okay, computers have been used to exhaust a finite number of cases, like the 4-color problem in combinatorics. but they cannot exhaust the infinite case. So again, that's where you've got to have the math step in and say, okay, the abstraction will take us to the result because the computer only does a finite number of computations. And it might be a billion of them, but that's still a finite number. Even though we can't even fathom how large that number is, it's still less than infinity. So this is a very powerful technique, and I hope that it's been kind of interesting to learn about it. Now, we keep using parts of the binomial theorem, so maybe at this point it would be good to actually uh, pinpoint it. That is, when you get to Cal 2, you're going to learn a more generalized version of it. So now what we want to do is get the version that basically covers the cases that we have used, the number 2 case where we square the binomial, and the number 3 case, which we've used many times during this course, where we cube the binomial. So let's just say, is this valid? We're thinking this must be a proof about natural numbers when we just focus on the positive integer exponents, and it is. So we can say, we can just call this binomial theorem, at least in as much as what we're going to do for now. And then when you get to calculus 2, you'll do a more generalized version. So what I want to do, first I want to define a binomial coefficient. So we're going to fix n in the natural numbers, and we're going to set k a natural number such that, in this case, k will run from 0 to n. And then the binomial coefficient and here's the notation we use, n choose k. And when you get to calculus, these numbers will be flipped because of just convention. So sorry for that. It just really depends on how things are set up. The binomial coefficient n choose k is defined as the following. That is, we'll say n choose k, and there are many ways to do this. One way is through factorials, which has its uses theoretically, but computationally is a little bit untoward. But it can be defined as n factorial over k factorial times n minus k factorial, which is kind of a train wreck with computation. So the one form that I prefer is the falling factorial. That is, we can write this as n perm k, which means the falling factorial of k factors divided by k factorial. So basically, this numerator will take the place of these two guys here in our function, and we'll keep the k factorial, which by itself is reasonable. And so we get the falling factorial. And this is very useful in calculus, especially when the upper number is not a positive integer. We get n times n minus 1 times n minus 2, and we descend to the nth factor, and excuse me, in this case, the kth factor. This is n minus k plus 1. I've been teaching the binomial theorem in calculus 2, and like I say, we switch the k and the n. How funny. So we have n minus 1, n minus 2, and then n minus k plus 1 divided by k factorial. So the idea here is that when you're actually computing the coefficients here, it's much simpler to think of it in terms of these factors because they're easy to write down. If that's a 2, then you're going to have just 2 factors here, 1, 2. If it's just 1, then you have the 1 factor right there. So the key here is that this is all hinging on making sure that this makes sense. So for this to, not always give us something that's undefined, we have the following definition. We define, to keep all of this to make sense, 0 factorial will just be 1. That'll be a convenience that'll make sure that we don't divide by 0. So when we think of 0 factorial, we're gonna define it to be 1. And then of course, k factorial or n factorial is just the falling, but it goes all the way down to 1. n minus 1, n minus 2, and then we just descend all the way to 1. So when you have the n perm k, this stops at k factors. That's the k factor right there. This one just has n factors, goes all the way down to 1. So this is like n perm n, where you just start at n and you end at 1. So the factorial is what you already know of. 3 factorial is 6, 2 factorial is 2, 4 factorial 24, 4 times 3 times 2, etc. And it's recursive. So we basically see that n factorial is just n times n minus 1 factorial. I mean, you can just say n and then that's n minus 1 factorial. So you can factor this and break it down into convenient pieces depending on what the problem requires. So the factorial function is recursive, and again, it very useful because not only does it come up in obviously analysis, as we see here, it's also very important in counting and combinatorics, probability type examples. So again, when we look at this, we're thinking, all right, so let's just kind of look at this in general. N, choose N, is another kind of odd looking one, but when you think about it, when you have N choose N, this will be N perm N divided by N factorial. But like I said, N perm N is just all the way down. This is N factorial over N factorial, which is 1. So these are always easy. If you have N choose N, 3 choose 3, let me move Professor Ron over. Get the focus, there we go. IPEVO improvement in the software, very good, always happy for that. So here we go. So these are like the extreme cases of the Pascal's triangle. N choose N, 5 choose 5 is 1. 4 choose 4 is 1. We can think of this like subsets, and I'll say more about that. 10 choose 10, 1, always 1. And then another convenient one using this, N choose 0. This is where you just have to say, what are we going to do with N choose 0? We're N perm 0 kind of thing. So we define this to be 1. These are the extreme cases. This one we can kind of eke out by definition, but it's like we're not writing down any factors of n and dividing by 0 factorial. So this is where we define this to be 1. So 5 choose 0 is 1. 10 choose 0 is 1. 500 choose 0 is 1. So these are what we call the extreme cases. So don't let these be an issue for you. Just know that when you have n choose 0, that will be defined to be 1. And n choose n is always 1 just by definition if we assume this. This one is really kind of odd because we don't really have anywhere to go with it unless we go up here. So if you think of it in terms of this would be n, for instance, if we just avoid that and we think, what would this be if we looked at the first definition? This would be n factorial. And then we'd have 0 factorial divided by n factorial, which again, this would just be 1. So however you look at it, you can either think of it as a definition or just eking through this, assuming that. Either way, you get 1. So the extreme cases, which will be very convenient, will always give us 1, okay? So one thing that's very nice about this that we can already see, you can see here that if we replace k with n minus k, it's not going to change this definition. So this definition has a nice symmetry about it. So if this became n minus k, that would be n minus k, and of course that would become k. So by symmetry, we don't even have to work to get this, and this turns out to be a big plus in computation. By symmetry, n choose n minus k equals n choose k. And basically, if we just follow that rule, we don't even have to look at this, which would be more complicated, even though this is very useful to do proofs. We just say, in this case, y. So we'll just use the first definition, n choose n minus k will just be n factorial divided by n minus k factorial. But now, of course, n minus k is just k. Well, let me just write it down. N minus k factorial. So this is n factorial, n minus k factorial. And of course, now the n's absorb and we have a minus k, so that's k factorial right there. So that's exactly this. You can commute real numbers. So this is exactly n choose k. So if you think about writing the definition this way, this certainly has benefits on seeing the symmetry of the binomial coefficient. At least n choose n minus k will always be n choose k. This is very powerful. For instance, if we had 10 choose 9, which would be a nightmare to compute this way with all those factors, we'd say, okay, well, this is the same as n choose or 10 choose 10 minus 9, which is 1, and that just equals 10. So this is easy. So we will often use this identity here because it simplifies. For instance, the smaller the number, the second number, the easier the computation, just fewer factors. So this is a very big help. Here's another example. 7 choose 5 equals 7 choose 2. Again, 7 minus 5 is 2. Using this identity here, we can easily compute this, which is much simpler. So now we can say this will be 7 perm 2 divided by 2 factorial. So this is 7 times 6 divided by 2 times 1, or just 2. So this will be 7 times, well, these absorb to give us a 3, and that's a 21. So at least computationally, when we're working with just integers or positive integers, and then of course we have to consider 0 because these are extreme cases that we have with binomials, we see that there's a certain simplicity that is given to us if we use this particular identity to make the computations easier. Of course, sometimes you get stuck with numbers that are just large, and that's just the way it is. So what besides this one, okay, so we have a very simple identity here. There's one more that's actually very important that allows us to work with binomials, and it's called the Pascal identity. So I want to write that down. So this is an identity due to Pascal, and the triangle that is utilized that has all these nice symmetries in it gives us some really nice coefficients for the binomial theorem. So I'm doing this all as preliminary to binomial theorem, otherwise it won't make any sense. So here's another nice identity. N choose k minus 1 plus n choose k. And this one's not very obvious. You can't kind of look at it and say, well, I can see that. It's not obvious. So the Pascal identity basically says that if we say n choose k minus 1 plus n choose k is equal to n plus 1 choose k. So you can often think about binomial coefficients as keeping track of the number of subsets of size k extracted from a set of size n. That's a nice probability theorem. But there are times when that is good to a certain extent, but the proof is harder than just fleshing it out using the algebra. It's kind of like trying to teach little people about fractions, and the technique you're trying to teach them is harder than just showing them how to do it. You know, it sometimes we try to make something so simple that the strategy of teaching it is harder than the actual principle we're trying to teach. So you have to find a nice medium here. So when you look at this and you think about this particular setup here, let's just look at it algebraically. So we'll say, why is this true? So this will give us some practice with our definition of the binomial coefficient. So let's go ahead and write down what this is. So this one will be n perm k minus 1 divided by k minus 1 factorial plus n perm k divided by k factorial. Okay, so this is just using the falling factorial that we had before. We could use the first definition, but this is actually pretty simple. So this is the left-hand side that we're working with. We're going to show it morphs into that. So now let's write it down. N minus 1, n minus 2. Then we descend to n minus k minus 1 plus 1. That's just replacing the k with k minus 1 in our definition, divided by k minus 1 factorial. And here we'll do the same. This will be n minus 1, n minus 2. Just put down enough factors so you know what the pattern is, down to n minus k plus 1, and then k factorial. Okay, so that's the definition I gave you at first. Now notice here, when we reduce this, what does this become? This is n minus k plus 1 plus 1, which is n minus k plus 2. So what we're seeing is that this is the factor that comes right before this one. These all decrease by 1. So this factor here is the one that precedes this factor. So all of these factors are common to both, so we're going to use that to factor things. But in order to combine them, we need a common denominator, right? So we're going to have to multiply this by k, so it becomes a k factorial. And then I can write this in a way so that you can see that this is actually embedded right here. So this will be k times n minus 1 times n minus 2 to n minus k plus 2. And of course, now we have k times k factorial. So remember, oh, that was the last problem. Picked up the wrong sheet. We just use this. K factorial is just k times n, or n factorial is just n times n minus 1 factorial. So just change out the letters. I know that's obvious, but sometimes it's just good to see it. All right. So when we look at this, we're thinking that at least at this particular juncture, k times k minus 1 factorial is just k factorial using the identity I just stated. And then over here, we're good to go. Let's just write it down, but then we'll stop. We'll go ahead and put in that factor that precedes this one so we can see that they have common factors, actually a lot of them. So we'll just go ahead and insert this so you can see the preceding factor. So this is just simple algebra, but it's certainly algebra that requires some college algebra and a more advanced standing that you all have. So now we can see that common factors just abound. right here, and all the way down to here, and then of course here and here, okay? So we're going to extract that. So now we have n minus 1, n minus 2, to n minus k plus 2, and we'll eventually rewrite that to reflect an n plus 1. We'll have the power to do it. And this has the k factorial. And then, of course, what's left over? K plus n minus k plus a 1. So when we look at this, the k's absorb, and we're just left with the n plus 1, which is exactly what we want. N plus 1. So now the n plus 1 can just be moved up to the front, and we've got it. So now we've got what? N plus 1, n minus 1. I won't have to write so many factors now, you see the point. And then, of course, I'll just write the n plus 1 barring one of those 2's there. So this will be n plus 1 minus k plus 1, which fits the standard definition of the first number, the second number, plus the 1. And then, of course, downstairs, we have k factorial. So now this is exactly this. N plus 1, choose k by definition. So by definition, we have what? N plus 1, choose k. So the reason I'm going through this is because this is of critical importance here. Just like the symmetry one that we talked about. This actually generates a finite sum that is amazing. At least it will generate sums indirectly, but basically what it does is it creates a triangle that has been attributed to Pascal. Pascal did a lot of work with counting, calculus, number theory, probability. He was one of those mathematical gurus that knew no bounds. And the thing is, his work is well documented. And just like the contemporaries of Newton and Leibniz, they all worked on the calculus. So everybody had something to do with making calculus terrific. It's just that there are 2 people in history that get credit for actually writing it down. So now let's see what we can do with this. So when it comes to the Pascal identity, we can now use all the tricks and facts that I've already given you. So we can now look at some very simple things. And here's what I want to do. We're going to start with 0, 0. Okay. We know that's 1. So I'm gonna put the corresponding over here. This is 1. And then we're gonna create triangles. Then we're gonna do 1, choose 0, and 1, choose 1. So remember, when we started all of this here, n choose n, 0 choose 0, 1. And then, of course, n choose 0, always 1 for any n. So this is what I'm using for the extreme cases, and that's why I wrote that. So 1 choose 0 is 1, and 1 choose 1 is 1. So it's like we're doing n equals 0, n equal 1, and then we're going to have 2 choose 0, and then 2 choose 1, and 2 choose 2. Well, if you look here, this is just Pascal. 1 choose 0 plus 1 choose 1 should be 2 choose 1. We just proved that. So that should be 2, shouldn't it? 1 plus 1 is 2. So Pascal right there. So 2, and then of course these are extreme cases, 1. So we're creating a triangle that has a bunch of 1s on the outside legs. As far as those two legs, they're always going to be ones. And then, so now you can see the method. So we have 3 choose 0. Now again, we're going to have Pascal 3 choose 1, 3 choose 2, 3 choose 3. Well, the outside ones are just extremes. They're ones. So we have a 1, but what's 1 plus 2? That's 3. What's 2 plus 1? 3. There you have it. 1, 2, 1, 1, 3, 3, 1. Those look familiar, don't they? Now, of course, whatever the binomial expression is, they can change these coefficients, but these will always be there multiplied by the powers of the terms from the binomial. So it was not at all haphazard that things turned out this way. Okay, that's the formula we just used in our last induction proof. So again, all tied into Pascal's work. So 4 choose 0, Pascal, 4 choose 1, 4 choose 2, Pascal, 4 choose 3, Pascal, and then of course 4 choose 4, which is extreme. So we have 1, 4, 6, 4, 1, etc. So we're thinking that these rows give us coefficients for binomial expansions. When we cube a binomial, we have to have these coefficients, regardless of what we get from the expression 1, 3, 3, 1. When we square a binomial, we have to have these coefficients 1, 2, 1. Of course, first degree, well, 1 and 1, that's easiest. Now for fourth power, we're going to have a 1, 4, 6, 4, 1. So you're thinking we can extend this triangle indefinitely. And so lots of times students will say, well, I'll write down the triangle and I can figure out the coefficients for 4 or 5 with relative ease. Okay. Of course, when the numbers start getting really, really large, you may only be required to write down a particular term in the expansion. So when we think about this, we call this Pascal's triangle. Pascal's triangle. And we'll see how it works. So now what we can do, let's just go ahead and add some more rows. Let's just make it simple. Just add a few more rows using Pascal's identity. 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So you see we're just adding using Pascal. That's why we orient the numbers this way, so we can easily use the identity. Then 1, 6, 15, 20, 15, 6, 1. Now what you see here is a nice symmetry. See this nice symmetry going on? Wow, look at that, look at that. And then we have 1, 7, 21, 35, 35, 21, 7, 1, etc. Let's do one more. Not that we'll ever go this high. We will, but we'll just look for one term. 1, because this has its limits, 8, 28, and then we have what, a 6, a 56, and we have a 70, and then a 56, 28, 8, 1, etc. So this, again, Pascal. Pascal, all of these done the same way. Pascal. See that? So this at least gives you a way to generate some coefficients quickly if you need it. All right. So basically, when we do this, we're actually drawing this triangle with binomial coefficients. And here we just replace them with their actual numeric equivalents using Pascal's identity. So when we're looking at this, we're actually viewing a triangle of Pascal or of binomial coefficients. So that's what this triangle is. So now we can state the binomial theorem and you won't think that I'm just making it up. So this is fun. and a nice way to give you a springboard into calculus 1, 2, and 3. So here's the theorem. Here's the binomial theorem. So I'll write it this way: fix A and B, and these can be any expressions, real numbers. We'll just deal with real expressions for right now. And we'll fix N, just like we had before when I talked about the binomial coefficients, where we set K to be a natural number, where K runs from 0 to N. Then, now we can write down what it means to raise A plus B to at least, at this point, a positive integer, N. And we can write it as a summation. So we'll use K equals 0 to N. So this is a partial sum. So we have N choose K. So now that's not a surprise. That's not a surprise. The N choose K just keeps track of how many copies we have of each expression in the expansion. It's like when we have the 1, 3, 3, 1, we have 3 copies of A squared times B, and we have 3 copies of A times B squared. So the binomial coefficient just counts the number of terms in each expression in the expansion, which we've been doing all along. And what do the terms look like? Well, here's one way of writing it: A to the N minus K, B to the K. Okay, so this is what we've seen before. That is, we generate expressions in this particular case that give us powers of A and B, but note the powers of A and B always add to N. N minus K plus K is N. So that kind of gives you a little recipe for writing down the expression. So what does all of this look like? Well, let's just go ahead and expand it. When K equals 0, we have N choose 0, A to the N, B to the 0. So that just, again, by definition 1, we get that term. N choose 1. Now we have A N minus 1 times B to the 1. And then K equals 2. N choose 2. A to the N minus 2 B squared, etc. Down to the very last one. Well, if you want, we'll just do N minus 1. Let me give a little bit more room here. So I'll go ahead and mark these out. K equals 0, K equals 1, K equals 2. Then we'll do K equals N minus 1. So we have N, choose N minus 1. And so now this will be N minus 1, which equals 1. So I don't have to write all of that here. So that'll be A to the 1, B to the N minus 1. And then the very last one will be K equals N, which will be N choose K, which will mirror this one, the extreme. Excuse me, N choose N. Let me write it in terms of the value of K. So these are the extremes like we have. So these are just coefficients along a row of Pascal's triangle. And so that'll just give us B to the N. So we see we have the extremes that we have from the triangle, and then we just move in symmetrically. This equals this equals this. These coefficients are equal, and we just start pairing them all. It's kind of like, as you see the triangle here, if you start pairing things off equal, equal, equal by itself, equal, 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 equal by itself. So all of the mathematics that you see here is based upon the theory of the binomial coefficients. And what we see again is that the triangle just gives us all of these coefficients here. Now, of course, A and B may have additional numbers in them, and we'll have to deal with those on a case-by-case basis. So you see here that when we think about a binomial, even if we just multiplied things out by brute force, which again is a counting argument, which would still produce these binomial coefficients, even like I say, if you looked at this from a combinatorial perspective, you get the same output, you get the same result. So again, this is something we have been doing all along. The binomial theorem we have been using, or you have been using since Algebra 1, but I doubt it was ever stated in this degree of generality. So now let's use it. Let's use it to solve some examples. Now, of course, the first thing you can do with binomial coefficients or the expansion is just to expand things, and you already know how to do that. So we'll do a few of these, but first, I just want to utilize some of the constructs that we have from the theory that we've already developed. So example, let's just do something really simple just to remind us of something we've already done before. So we'll just say, here's a simple expansion. So we'll say expand using the binomial theorem. So I'll just say we have something like this. Say we've got, and we can do this a very simple way. So we've got the following. So we've got, I'll throw in a 2 just to make it interesting. 2x minus, let's say we'll throw in a y. We'll say minus y to the 4th power. So now we'll just do this as 2x plus a negative y. So we've got our a and our b raised to the 4th power. Okay, so this may be something that may be of interest in a problem. Again, just something that's academic. So you're thinking, well, you could say 2x minus y times 2x minus y times 2x minus y times 2x minus y in brute force. Okay, that's certainly, and I've had students do this on a final exam, and I pretty much had to mark it wrong because I said, use the binomial theorem. So if you don't use the binomial theorem on your final exam, it won't be correct. Okay, I know you already know how to do it by brute force. If you don't use the binomial theorem, then you have not bothered to learn this result. So I'm just warning you now that if I say work a problem using the binomial theorem, use it. Otherwise, you can. If I don't say you can do it by brute force, but it'll take you much longer. So just be careful to remember that if I say use a particular theorem, I need to see it. Otherwise, you're free to do whatever. So you have that luxury if it happens to arise. So now let's go ahead and fill this in. Notice we'll do a little sidebar over here. I thought it interesting how you all did your conic sections. You just did a summary of everything that, like I did with the law of cosines and sines, which actually was pretty good. So we've got A equals 2x. We have B equals the additive inverse of y if we're going to fill in the formula. And then, of course, n is equal to 4. Okay? So now by the theorem, we have k equals 0 to 4. 4 choose k. And now we have what? 2x to the 4 minus k negative y to the k. Okay, so that's just filling in the binomial theorem. N is 4, A is 2x, B is negative y, and k runs from 0 to n, or 0 to 4, just like I stated in the theorem. So now let's go ahead and flesh this out. So this will be 4 choose 0. And if you like, we've got what? 2x to the 4th. That'll just be 0, so negative y to the 0, so leave that out. Plus 4, choose 1, 2x. Now we have 3, 4 minus 1, 3. Then we have negative y to the first power plus 4, choose 2. Now we have 4 minus 2, so we have 2x squared, negative y to the 2 squared, plus 4, choose 3. Of course, 4, choose 3 equals 4, choose 1. So this will be 2x. Now, of course, we have 3, 4 minus 3, 1, and then negative y to the 3 right there. And then lastly, 4, choose 4. So they got 2x to the 0 by definition 1, so you can leave that out. And this would be a negative y to the 4th. So if you like, these are easy coefficients. I mean, we can easily compute them, but you can already just say, if you just wanted to do a quick triangle, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So they're the coefficients right there. So of course we have 1. So this will just be what? 2 to the 4th times x to the 4th, because that's just a 1. You can just say 1 times plus. Now 4, choose 1, that's 4, or just compute it directly. 4 times 2x cubed, 8x cubed. And then we have times a negative y plus 4, choose 2. That's just 4 times 3 divided by 2, which is 6. So we have 6 times 4x squared. And then negative y squared is just y squared, the negatives absorb, plus 4, choose 3, which is 4, choose 1, which is 4. So we have 4 times 2x. And now we have times, of course, the negative survives, negative y cubed. And then lastly, 4, choose 4, that's extreme, like 4, choose 0, that's 1. So we have plus 1 times, and then of course, a negative 1 raised to the 4th power absorbed, so we get y to the 4th. Not a surprise. So now what do we get? Well, 2 to the 4th is 16. So we get a 16 x to the 4th. Now, of course, we have the negative here. So 4 times 4 times 8, that's a 32. So a negative 32 x cubed. Now here we have the x squared times the y squared, 6 times 4, that's a 24. X squared, y squared. Now, of course, here we have the negative, 1 times 8, negative 8, negative 8x y cubed, and lastly, y to the 4th. Now, the thing about the binomial expansion is that it combines the terms for you. Now, of course, you can multiply all this out by hand, but as the power gets larger and larger, this becomes much more powerful. So again, what do these binomial coefficients do? They collect the terms that look like that. There are 4 of them. The terms that look like this, there's 6 of them. The terms that look like this, there are 4 of them. And there's only one that looks like that and only one that looks like that. So the binomial theorem does a lot of the work for you. I mean, it clearly you got to work, but what you're seeing here is that it is a powerful result. The real power comes into the calculus version, where this is not a positive integer like 1/2 or 1/3, and then you actually start to understand the infinite series that proves why your calculator can take strange powers and give you a decimal approximation. Ladies and gentlemen, the calculator works because of the calculus. The calculus is the backbone of any calculator. So that's why I consider it quite a luxury when we can go to the Google calculator and get a really nice calculus approximation after we've already done all of our work. So here is the most basic use of the binomial theorem, ladies and gentlemen. It's just like, okay, this is what you've been doing. You take a binomial, you raise it to a power, and it tells you the recipe to do it. This is a statement about natural numbers, okay? So you could prove this result by induction. And you can also prove it by a counting argument. And if we have time, I may say something about that. But for right now, I wanted to spend more time on the binomial coefficients and Pascal's identity so you actually know how these interrelate and that they do come together to give you a very nice cogent result. Okay, so let's do some more examples. Simple, but useful, and anything that makes our work easier, we like. Now, here's an example that utilizes the power of the binomial theorem. Here it says, compute the 25th term. Compute the 25th term of, and you're thinking, well, this is easy. This is just generic a plus b to the 26th, okay? Now, here's what's interesting about the binomial theorem. We start with k equals 0 and we end with n, okay? So they're always n plus 1 terms. So note here, and this is very important, and we're using the convention of the way we've stated our theorem. So this is, again, like doing the conic sections. We'll say the 25th term corresponds to the index k equal 24, because remember, we start with k equals 0. So we have k equals 0, 1, 2, all the way to n, which is 26. So this gives you 27 terms. So the key here is just noting the way we've set up our construction. So you don't have to guess. You can always look at the algebra of the coefficients and figure it out. But this way, this makes the problem more abstract, and and you're thinking, well, I could just expand this setup. No, you can't. You would lose your mind doing that. Okay, so the idea is that now we use the power of the theorem. So here is the general term. Let's write it down. General term from our binomial theorem. And that looks like this. N, choose K, A to the, so nice we have A and B. That couldn't be any simpler, right? B to the K. So now we're going to set N equal 26 and K equals to 24. So this implies, here's the term right here. So 25th term equals 26, choose 24. A, I'll write it out, 26 minus 24, B to the 24th. Now, you're thinking, well, that's the easy part. And now using the identities I've shown you, we can make this a lot easier. So this turns out to be a simple problem if you use the construction of the what? Binomial theorem. So again, this is too difficult. So 26 minus 24 is 2. This just gives us much fewer factors. So this is using the identity that I gave you initially, the symmetric identity. And then we have a squared b to the 24th. So the 25th term has this expression of a and b. And now this coefficient is going to tell us how many do we have of a squared b to the 24th, because this counts the number of them. So let's write it down. So this will be 26 times 25 divided by 2 factorial, which is 2 times 1 or 2. So boom, right there. So again, remember the binomial coefficient, 26 perm 2 factors starting with 26 divided by 2 factorial. a squared b to the 24th. So this, of course, that'll give us a 13. So this part gives us a 13. So we can write that as 10 plus 3 times 25, a squared b to the 24th. So that'll give us what? 10 times a 25 is a 250, and 3 times a 25 is a 75. So when we add those, we get 325. So we actually have 325 copies of the term a squared b to the 24th. So this is definitely a counting argument when the power is a positive integer. It becomes a counting argument. So many disciplines can treat the binomial theorem simply in this light as a counting construction in discrete math or combinatorics. So the beauty of this is that you will get to see the binomial theorem in many different lights. And then, of course, the identities that we've talked about with binomial coefficients, there are tons of those. So if you ever want to look up the Wikipedia page or look in a combinatorics book about binomial coefficients, you will stay very busy. There's so much information on these topics that it just boggles the mind. And now with our technology age, you can easily find it. So again, the power of the binomial theorem just to select a particular term. Very nice. Could not do that before. And please don't expand all of those terms by hand. You could do it, but it's not. Again, I could have you write down the expansion, and that's fine. All we did was just select one term, which was important to this theorem. So if you can do this, you can write the expansion down, like we did for the last problem. Now, before there's a nice homework problem, but I want to do that. I want to do that a little bit later. Let's see here. Actually, it actually will probably work now. I won't hold off on it because I've said some things about factorials, so this is good. So let's just move into more number theory right now. What I want to do is compare the numbers. So binomial theorem opens the door to lots of ideas and also how we can think about binomial coefficients and factorials. So here are the two numbers we have: 140 factorial raised to the 141st power. This is kind of rigged, but an interesting problem. And we have 141 factorial raised to the 140. Now, when you look at this and you look at this problem, what you want to do is compare the numbers. And of course, these are written in ways that we can actually compare them. And I think your homework problem says which number is bigger. And so you're thinking, well, I've got a fancy calculator, Professor Ron, and it might blow up if I try to evaluate these. That is clearly not the way to do it. And then, of course, that's like having doing your support for your trig test, and you typed a bunch of decimals on your paper, and you're saying that's the answer, and it's equivalent to this exact result. Well, you know how many points you get for that. So I would say when you look at something like this, you approach it the same way. You use the fact that you understand factorials and laws of exponents. So here's one way to do this. Let's just compare these as ratios like we're working with the geometric sequence. And boy, the geometric sequence is fun. That's a beautiful result. Again, we can't do without it. We need it. So 141. And then we have 141 factorial to the 140. This is how I actually set this up, and it actually turns out to be an interesting way to look at it. Now notice, and this is what makes this simple. With the laws of exponents, we can break this up into a power of 140 plus 1. So let's do that. So this will be 140 factorial to the 140th times 140 factorial, okay? So now when we look at that, we're like, okay, that at least breaks this up so the powers are the same. And so downstairs, what does that give us? So we have 141 factorial. Wait, let me write it this way. Let me put the factorial inside. So this is just bookkeeping at this point. Okay, so now when we look at this and we think, okay, so how does this help us out? Now, of course, now we can use laws of exponents right here on this part. Laws of exponents. So now this gives us 140 factorial. And now, of course, remember, 141 factorial is just 141 times 140 factorial, the same identity I gave you at the very first of the lecture. So this is 140 factorial times 141 by definition. And this is raised to the 140th power times, and then we've got this rogue term over here, 140 factorial. Now, when you think about this, and here's another thing that's kind of interesting about this. When you think about it, what's interesting is that it looks like a lot of this is going to go away, but then you're thinking, how we're going to work with what's left? Well, let me show you. These absorb. So now we have what? 1 divided by 141 to the 140th times 140 factorial. Now, here's the interesting thing about this. This tells us the answer right here. Let me tell you why. When you look at this, this gives you all the factors starting at 1, 2, 3, all the way ascending to 140. And all of these factors here are bigger than every factor in this. So, and there are 140 of them. So now if you wanted, the key here is that this exceeds all the factors here. So this quantity is actually less than 1. But let me show you why. You can do 1 times 2 times 3 times 4, and then dot, 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 139 times 140. That's what 140 factorial looks like. And then you can pair it off with downstairs with a 141. And there are 140 of those. And every one of these numbers is less than 1. This is what I do in calculus. And maybe if I did more of this in pre-cal, the students would have an easier time, but I don't know. I think by the time you get to calculus, you forget everything I tell you. But the thing is that these numbers are all less than 1. So in product, the entire expression is less than 1, using properties of real numbers. We know this with the binomial series. And when you get to calculus, you'll even look into this more closely. That is, when you raise a number in absolute value less than 1 to any power, the result is always less than 1. That's geometric. And so when you look at this, you're thinking, okay, all we've done is use laws of exponents and Professor Ron's definition of factorial, which I've used. It's interesting how I think by now you can see I introduced the concepts to you that are important, and I use them in my lecture. Ladies and gentlemen, I will never waste your time. I never waste your time. The key is that I know what you need to know. And if you put the ideas together and work with them and stress your brain a little bit, you will become better. And I see that with a lot of you. So I appreciate that. But remember, STEM professionals must strive for greatness because you will change the world. And I know I'm a broken record, but when I finally believe that my students have listened to that and heard it, I'll stop. But it's still not that way. But for some of you that already know, excellent. So everybody, if this ratio is less than one, the number downstairs must be bigger. So by analysis, this implies that 141 factorial to the 140 must be greater than 140 factorial to the 141. So that's an analysis that we can do using what we know about factorials. So what has been so important to us as we move through this class? The exponential functions, the power functions, power rules, laws of exponents, that they are so intrinsic to doing real analysis. We can't do it without them because they provide the recipes to combine expressions in a multiplying strategy. When we multiply, when we look at factors and we consider the laws of exponents, they become the basis of how we move our arguments forward. And we saw that very neatly in the binomial theorem when we've got these powers of A and B raised. You know, we've got powers of A and B. I don't have to say raised, I've already said powers. And then we use our understanding of real numbers. That is, if we take the product of -1 an even number of times, we get a positive result. If we take it an odd number of times, we get a negative result. So using the qualities of the real numbers with the laws of exponents, as we synthesize those, we actually see that we can get this type of analysis. So I'd like you to spend some time on this and master this. These make great test questions. And again, the beauty is that you don't have to even do anything except think of this like you're working with a geometric sequence and look at the ratio. Here's a good trick, a good strategy in the future. If you're trying to figure out which particular expression is larger numerically or whatever, look at the ratio and then, operate on it and say, oh, okay, this ratio is less than one. So the bottom number must be bigger. If this is greater than one, then the numerator is bigger. So this is a nice technique that you can use and is very, very useful in other courses. So not just here for this particular problem. Okay, good. Now there's some nice results for the binomial theorem that I want to use. Lots of times when it comes to results, we're interested in, okay, so if we've got this binomial theorem, because right now Professor Ron's been focused on, okay, factorials, Pascal's identity, how it impacts binomial theorem expansion, and then picking out a particular term. So you know how to do that. But here's some other series that may be of interest to you. Here's one right here. For instance, consider, now that we have the binomial theorem, the following, the finite sum. So what we're going to do is fix in element of the natural numbers, okay? Fix in element of the natural numbers. So we're going to look at the following. So this is going to look real familiar to you, and you're going to tell me what it is, or I'll ask you about it. So what we're doing here, and you're thinking, oh, well, that's not too bad. What does this actually equal? Well, this would be, we can think of it like this. K equals 0 to n of n choose k. So that's kind of a hint. I'm writing it that way. So when you look at this sum, you're thinking, oh, I see what you've done, Professor Ron. You've added a row in Pascal's triangle, and then you wrote it with a sum. So we can basically say sum of elements in the nth row of Pascal's triangle. So when you look at this, you're thinking, oh, okay, so that this could be like, 7 choose 0, 7 choose 1, 7 choose 2, up to 7 choose 7. And then when I write it this way with the sigma notation, you're thinking, that looks kind of interesting. So how could we get this from the binomial theorem? And here's the way to look at this. We think, well, these are undisturbed. There are no other coefficients hanging around. So now when we look at this, we can think, what's really going on here? So we'll do one more step, and I'll let the cat out of the bag. So this is more of a discovery problem than me just telling you what the answer is. So we could do n choose k, and then we can say, all right, well, let's just go ahead and say what 1 to the n minus k and 1 to the k. Okay, now if I put these ones in here, then there's no difference. I'm just multiplying by powers of 1, which is 1. Okay, so it doesn't change anything. These are equal. But now you're seeing that we have opened the door to the application of the binomial theorem. So now you can say, all right, what does this mean? Well, this is just a statement of the binomial theorem where we have A equals 1, B equals 1. So this is the binomial theorem. So you're seeing that the power of mathematics usually is found when we actually work theorems in reverse. We think of the rational zeros theorem, we work it in reverse to get any use out of it. And then, of course, this is the binomial theorem in reverse, because this is the so-called expanded form, and we're thinking, how can we write this in factored form? Well, this is just a plus b raised to the n. So this will be 1 plus 1 raised to the nth power for the fixed n. But I think the last time we checked, 1 plus 1 was 2. So this is 2 to the n. So when you look at any row of Pascal's triangle and you sum the elements, if it's the nth row, the sum of the elements will just be 2 to the n. So we're thinking, okay, so you could have phrased this problem basically as don't even think about Pascal's triangle. And I could have just said this equals this. And then you'd say, oh, I see what you did. You said A equal to 1 and B equal to 1 in the binomial theorem. So now we can say, here's an example. So you can impress your friends and say, oh, I have the ability of Ramanujan. I can do the computations in my head. Lots of times when you observe someone doing something that looks really miraculous, and it is quite miraculous, but they are utilizing some mathematical construct that allows them to produce results quickly. And you think individuals who are very good at cards because of their ability to assess the probabilities. And again, that's a gift of arithmetic that not everybody has. So it's not always the fact that a good card player is not being honest. It might be that they are very talented. And if you go to Las Vegas, they don't want you to come back. It's like, no, you're winning too much money. So again, when you look at this, we could say, all right, well, let's look at the following. So we have 6 choose 0, plus 6, choose 1, plus 6, choose 2, plus 6, choose 3, plus 6, choose 4. I'm writing these all out just for the impact of the problem, so it at least has more relevance to you. You're thinking, well, Professor Ron, I could just go to the triangle and add them up. Fine, you can, but now we know that this is just 2 to the 6, and that's 64. So the key here is that sums like this do occur, and then in combinatorics, you actually look at finite sums of binomial coefficients. And when you do the binomial theorem in calculus, you will compute general terms of the expansion that won't be as user-friendly, but still very fun to do. So I thought this was an interesting result. Now we can actually flip this result. So this is something that's useful, again, that can be directly proven using the binomial theorem. So we can start this equals this, prove with binomial theorem, or just write the sum down and then work backwards and say, oh, the result lies in the binomial theorem. So that's a very interesting result. And now, what about something else? Then we'll do a probability problem. So here's an example. Fix n element of the natural numbers. And we'll say, consider the finite sum. So in this case, we might say, okay, so we've got the following. We have n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 plus n choose 4. And then we'll just do dot, dot, dot plus -1. And so here we'll just, let me do this. Let me write it in a way so it doesn't look like I just kind of left things out. We'll just say here plus, or do minus plus, since the next term would be a minus, and do it like this. Then I'll do plus -1 to the n 4. So let's just see that, well, let me write it this way. N choose n. Last thing I looked at, 4. So let's just see if this is the way I wanted to do it. So let's see, we've got what? In this case, this looks good. So we're alternating the sum here. And so when we look at this, we're thinking, okay, so this is the k equals 0. This is the k equal 1, k equal 2, k equal 3, k equal 4, and this is the k equal n. Now, when we actually extend to the very last term and we think about how the powers or the signs are evolving. So for instance, if we start out with 1 here, you know, and then we're looking here, we've got the 0 term. So let's just think of it this way. Let's see, this is the 0 term, and so that would be 1. This is the 1. And then, okay. So when we get to this point, this is an indeterminate deal here. And so if we say 0, and then we have the 1, and then we have the 2, and if we're following the k power, this will actually work. So if you work this backwards, we're kind of thinking of -1 to the 0, -1 to the 1, -1 squared. And then when we get to this point, we're just saying -1 to the value of k. So this will give us a general term here that's consistent with what we have here. So what I wanted to do was make sure that what I wrote down was consistent. So now we can think of keeping track of the actual sign of the coefficient by, in this particular case, raising -1 to the power of whatever the value of k is. So this makes sense. So of course, in doing this, I've given you reason to think about how to solve this. So now notice we've got what? N choose 0 minus n choose 1 plus n choose 2 minus n choose 3, etc. And then we've got Pascal's triangle again, but now we have what we call an alternating sum. This is what we call alternating, but it's finite, alternating sum. You're going to have an alternating series, and what it's going to mean is that the sign of the series alternates, and that the generating part is always positive, and you control the alternation in sign by a structure like this, by a mechanism -1 to a power. So it's like on, off, green, blue. It just goes back and forth, back and forth. Not like 5 of them are positive, then you have 2 negative, and then you have 500 positive like that. It's in a systematic way. So now you can see that this makes sense. So we might think about, okay, so if you look at this and you think, well, this is inductive, but again, this is Pascal's triangle. So let's go ahead and write this based on what I've done here. So we have k equals 0 to n. And now, if you like, we've got what? -1 here to the k, n choose k. All right? So we've got that. So when you look at this, you're thinking, okay, so now if we go back up here, k is 0, so that's -1 to the 0, which is 1. We have n choose 0, and then k is equal to 1. We've got -1 here, -1 to the first power, n choose 1, etc. So we have that. So we have this alternating bit, so to speak. Now let's just check it out. Let's just check it out. Notice this will take a little bit more analysis than the last one. Let's just write down a couple of these rows. So we're doing a little analysis here. So let's just look. Let's just say, okay, well, let's take n equals 1. So we've got what? 1 minus 1, that equals 0, all right? Okay. Let's look at n equals 2. So we'll do it. Remember, it's going to be alternating. This will be 1 minus 2 plus 1. Well, that's 2 minus 2, that's 0. Okay, so far, so good. N equals 3. Let's look at it. 1 minus 3 plus 3 minus 1. Well, if we look at that, what is that? There's a 0 that, well, 0, 0. So there's 0, 0. So basically, if we wrote this down correctly, this would be 1 minus 1 plus -3 plus 3. If we reorganize, commute, this is 0. Oh, okay. Let's try n equal 4. So here we go. So we have 1 minus 4 plus 6 minus 4 plus 1. Okay, well, we'll put the 4's together. So we've got what? 1 minus 4 plus 6 minus 4 plus 1. So now we've got, let's just go ahead and do it this way. Let's just associate as we move through. So we'll do this, this, and then this. So we have what? -3 plus, now we have a 2 plus a 1, oh, 0. Oh, okay. Okay, let's try it one more time. So we have 1, 5, 10, 10, 5, 1. Well, let's look at it. So this is going to be 1 minus 5 plus 10 minus 10 plus 5 minus 1. Well, let's just associate like we did before. That way it takes less work for Professor Ron. So this will be a negative 4 plus 0 plus 4. So now this is kind of saying, all right, it looks like we're getting 0 every time. What's going on here? I mean, how is it that we're getting this? And we're thinking, what's going on? Now, remember the last time we just threw in A equal 1 and we threw B equal 1. And we thought, well, yeah, that works. So we get the 1 powers of 1 times powers of 1 or 1 and no problem. So now when we look at this, we're thinking, oh, okay, well, what if we did the following? So by this analysis, this says set A equal 1, B equals negative 1. What's that going to do? So this implies from here, well, I'll just write this in red. So this implies we have what? A plus B to the n equals what? 1 plus, and we'll do negative 1. So we retain the positive sign here, the plus sign n. And so this will give us, in this case, we've got what? K equals 0 to n. And then we've got n choose k. We have 1 to the n minus k. And we have negative 1 to the k. But of course, 1 to any power here is just, as long as it's not a 0, that by definition, well, even if it is a 0, that by definition is 1. So this gives us k equals 0 to n, negative 1 to the k, n choose k, which is exactly what I wrote here. But now, which is not a surprise, but now we see that this is actually this, but what does that say? Last time I checked, 1 plus negative 1 was 0. So this equals 0 to the n, which is 0. Again, this is not indeterminate. If you take 0 and you raise it to a finite power, it is clearly 0. Now, when we have 0 to the infinity, that will be indeterminate because that's not something we know about as long in this case, for instance, if you have an expression that's getting really close to 0 and the power is approaching infinity, you don't know that the answer is 0. That's indeterminate. But here, we're just saying 0 times itself n times. But the last time I think we all read that story, we got 0. So what we're seeing here is that when we have this alternating sum, ladies and gentlemen, we get 0. So, what you have to do on occasion is to say, wait a minute, this is kind of the trial and error aspect of this problem. It's like, well, if I start adding the rows of the Pascal's triangle and I do it with the alternating sum, I'm getting 0 every time. Why is that? And then you're thinking, well, how do we do the last one? Well, we make an assignment that seems to support that. Let's take an A and a B that will hopefully give us this alternating sign mechanism here. But of course, two numbers whose sum is actually 0. And then we support not only this, but we support this. And we see the binomial theorem gives us the exact proof that we're looking for. So there are things about the binomial theorem that are just waiting to surprise you. It's like, bam, oh, I didn't know that this was the case. So this is what I want you to appreciate about the binomial theorem. Not only does it give you expansion capabilities, but now you can pick and choose the elements that you want to recover from an expansion without having to do the entire expansion. You can use it to factor things. You can use it to compute finite sums. And then, of course, this is just the beginning of this process. But now you can see that the binomial theorem has indeed a great impact. Now, there was one other interesting problem that I wanted to speak of. And this is a little probability problem which covers the binomial theorem. So here's an example. Say, let's just say that we have the following. Let x, this is like a Greek chi, I'll say let x equal number of successes in the game darts. So in the darts game, basically when you hit the bullseye, that's a success. So success that is hit bullseye. Okay, so when you're playing darts, this will be, well, I'll just say in the darts game. That'll make more sense. In the darts. How funny. In the darts game. Right there. And so what we want to do here, and here's a little probability. I'm going to say I've done some probabilities on a particular dart player, and they're really good. And we'll say that the probability of success, that is when one trial of throwing the dart is 9/10. So this implies probability of, and the thing is, with success we can say probability of non-success or probability of miss, lack of success, would just be what? 1/10, because we'll say that the probabilities must sum to 1, just basic discrete probability. And so I've got this really good dart player and they're really good. And so there's a 9/10 chance that every time they have a trial of throwing the dart, they're going to hit it. Pretty good odds there. The probability of miss, of course, would be 1 minus 9/10, which would be 1/10. So the thing is that we have what we call a probability distribution based on the binomial theorem. So here's the theorem right here, and it's called binomial. We'll say, in this case, and I'll just say here, fix. Let me write it this way, just like doing the binomial theorem. Fix n element of the natural numbers, and then set k element of natural numbers. You're thinking, well, this sounds like the binomial theorem again, and binomial coefficients with k running from 0 to n. So you're thinking k is going to keep track of successes. Then for the binomial distribution, this is binomial because you've got these discrete cases that for each trial you have a probability of success and a probability of sometimes they call this a failure. I'll say failure. I don't like that word, but I'll just say a miss. So the binomial distribution probability function looks like this, and I'll use the k up here, or the chi, probability that we have, in this case, k successes. So for instance, if k is going to run from 0 to n and you've got n trials, so like say maybe there were 10 trials, and we wanted to know the probability that there would be 3 successes. And for this particular p, that would be pretty good. We would say, okay, that's binomial, and it looks like this. N, choose k, you're thinking, oh, boom, here we have it. P, in this case, we're gonna flip things around. We're gonna say k, we're gonna put that first, and then the q will be second n minus k. So for k successes, we would want the probability to be raised to that power, okay? For k successes. So now we're kind of flipping the A and the B around, but they're perfectly symmetric. So it says the same thing. So again, when you think about the binomial distribution for successes and failures, it is exactly the binomial theorem, except now we're only looking at one term, okay? Just like we did before, like what's the 25th term? This gives us the term that we're looking for here from the n plus 1 terms. And of course, if we added them all up, we get 1 because that would be the sum of all the probabilities. Okay, so think of this like doing the 25th term that we did back at the beginning of the lecture. So now we can say using these probabilities. So again, let's do it this way. Let's set this equal to P, which is the probability of success, little p, and little q, which is the probability of a miss. So in this case, let's take this example. So we'll say you're playing darts and you'll say, and let's just say that in this case, we've got, we'll keep it reasonable. We'll say that we have 5 trials, n is 5, p is 9/10, and q, of course, is 1/10. And you want to compute the probability. In this case, we'll say 3 successes. So the number of successes here would be 3. Okay, so now we'll apply the theorem. So probability that x equals 3 will give us, okay, so we have 5, choose 3. And now we have p, which is 9/10, raised to, in this case, we've got 3 for k. So now note here, this just says k equals 3. So we have 3, just like I have here. And then n minus k is just going to be what? 5 minus 3, which is 2, right there. Okay? So the key here is that when you think about a trial or an experiment, and there are 2 outcomes. You throw the dart, you either, boom, you hit the bullseye or you don't. You either succeed or you miss. That creates a binomial distribution. And the thing is that it's exactly the binomial theorem that we've been talking about. Now, some of you may have studied this in finite math or in a statistics class. And if you do discrete math, you'll go back to this. So this is a nice application of the binomial theorem. So now, boom, there it is right there. That's it. That's the probability right there. So let's just, see what we get. Just work it down a little bit. Now, of course, 5 choose 3 is 5 choose 2 because we're lazy. Right there. And then, of course, we get 9 to the third, 10 to the third. And then, of course, here we get 10 squared. Okay, 5 choose 2, we know what that is. That's going to be 5 times 4 divided by 2 factorial, 5 perm 2, so that's going to be a 10. So we have 9 choose 3, 10 choose 3 times 1/10 squared, or 10 choose 3, 10 to the third power. So that's a 10, obviously. So we get, I'll just move it down. So we have 9 to the third, 10 to the third, and then we have 10/10 squared. So this will give us 9 to the third. And then, of course, this will absorb, leaving us with 4 copies of 10. And now, of course, 81 times 9, that'll be 729, or 81 times 9 gives us 729, 729. And then, of course, here we've got what? 10,000. So with this particular setup here, with these types of distributions, the probability of 3 successes will be 729 divided by 10,000. And now here's something I want you to do for fun. Keep it all nice and exact. Do this for the rest of them. Compute for k equals 0, 1, 2. We've done 3, 4, and 5. And all of these answers that you get, when you add them up, you'll get 1. Because now you're seeing that here, what is this? P plus Q to the n here is just 1 to the n, which is 1. So by the problems we just did, this was a segue into this. You add all of these terms up, and you'll get 1, because if we add all the terms based on the experiment we did before this, we'll get 1 because the sum of P and Q is 1, because it's binomial. So now you can see that the binomial theorem not only has its impact in calculus, but also has its impact in probability theory. So I thought this would be an interesting little example. But what you can see is, with what we've done today, now you have more flexibility with binomial expressions. You don't have to just say, well, I'll just beat it to death and multiply it out term by term. You don't have to do that anymore. Now you have the luxury of Pascal's triangle. You can pick out a term without having to compute all of them, just like we've done. You can look at finite sums differently now. You can look at factorials, compare sizes of numbers. Now you know what a binomial coefficient is. So enjoy this. This is such a wonderful way to complete this class, because it allows you to just kind of sit back and say, you know what, this is enjoyable math. It's not overly tedious, and it's actually very useful. Mathematics has so many uses in life. Even if you're not in STEM, it is a truly rewarding discipline. It's kind of like doing something else, like say you really love English and writing papers, reading, or doing music. Professor Ron loves doing music too. And again, trying to balance two passions and gifts that you have in your life can be very frustrating at times, but your life wouldn't be complete without it. And so, of course, when you change the world, you have a tough life. You have a challenging life. But you know what? It's that challenge that gets you out of bed in the morning, and then you just surge to that success. You surge to make the world better. And that's what math allows you to do. It's such a rewarding discipline. So I'm glad that you were able to make it today. I'll have up some announcements about the final exam and about things that we have to do. Don't forget your signature assignment. That's due tomorrow. Again, that's just a simple problem on the law of cosines. Again, easy quiz grade. Enjoy it. If you want to work together, you can. Just make sure that you write up your own assignment, so to speak, as you put forth your work and your validation, that it's your work. But if you want to discuss this with other people, that's fine. You can't discuss it with me, but you can discuss it with your colleagues. So I appreciate your attendance today. I hope you enjoyed our little journey into the binomial theorem and factorials and binomial coefficients. So I'll send out invitations today for conference hours. So I'll look forward to seeing you. Good luck with your studies. Everybody take care.